The whole point in determining whether or not we have a function is so that we can use function notation. So anytime we have an equation that we recognize as a function, we're going to want to write it in function notation. So that's why it's important to solve equations for the y when we're determining if it's a function, because if it is, we're going to write it in function notation. So our function notation is that f of x. And we read it f of x. So it's f parentheses with an x in there. We read that f of x. And so basically all we do is remove the y and replace it with the f of x notation. So instead of writing a y, you write f of x. So anytime you see the f of x notation, just remember that that's the notation that indicates y. It does not mean that you're going to take the f and multiply it by x. When we see the notation f of 2 equals 3, that means that this 2 is our x, this 3 is our y. What's in the parentheses is the x value. What's on the other side of the equal sign from that f of x notation is the y. And we're going to have to evaluate functions. And so all that means is whatever's in that parentheses where you would have had the x written, you're going to replace it with whatever number or whatever thing you're being given. And then we're going to clean it up or simplify it. Let's get started on our examples. So here we have about 7 examples. We really don't need all 7, but we're going to use it to just illustrate a few things. So on number 1, they want us to find f of negative 1. Now there's 2 things we have to pay attention to. We have to pay attention to that they named it f, because we actually don't have to just name it f. We can name it g, h. We can name it r, st. So it's named f, so I have to find the one that's named f. And on here we actually have 2, one that's named f and one that's named g. So we're going to take the one that's f and we're going to use that one for number 1. And then the other thing it tells me is wherever you see an x, replace it with negative 1. So I'm going to write down that f of x notation. That function, f of x, just so that I can have it in front of me, because that's the one we decided to use because it said f of negative 1. So I wrote down the f of x notation for reference. Now wherever there's an x, I need to replace it with a negative 1. So the first thing I'm going to do is I'm going to write down what I had for f of x, but anywhere where there was an x, I'm not going to write the x. Instead, I'm going to write a parentheses. So instead of x squared, I have parentheses squared. Instead of minus 10x, I have minus 10 parentheses. And then I copy down that minus 3. Now inside those parentheses, I put my negative 1. And I want to use my parentheses every time, because then I go back and I evaluate whether or not I really needed those parentheses. And in this example, we needed those parentheses, because it says take your entire negative 1 and square it. So if you're trying to put this in the calculator, you have to use parentheses to put that negative 1 in the calculator. I need the parentheses here because I need to say that it's a negative 1 that's being multiplied by this negative 10. Subtract 10 means you have a negative 10. You're adding a negative 10. So let's clean this up. We can punch it up in the calculator, or we can use our order of operations. Using the order of operations, at some point we'll get 1 plus 10 minus 3. 1 plus 10 is 11. 11 minus 3 is 8. Our answer is 8. So see, it's not that bad. I'm going to do number 3, and then I'm going to come back to number 2. For number 3, it says f of x plus 2. So I'm going to the f of x. I'm going to replace the x with an x plus 2. So everywhere I see a x, I'm going to write a parentheses. And now inside those parentheses, I write x plus 2. And I kind of just felt like skipping to number 3 because when we're learning how to evaluate functions, problems like number 1 and problems like number 3 are more common. But we will need to know how to do stuff like what we have in number 2 and number 4. So where we have that x plus 2 squared, first thing I need you to understand or remember is because you have a plus sign right here, you can't just do x squared and then 2 squared. You have to write the entire parentheses twice because it's squared and multiply it out. If you don't have the plus or minus in the parentheses and everything is multiplication and division, then you're able to just take that square and bring it to each component inside of there. But that's not what we have. We have addition subtraction in there. We write it twice, we multiply it out. So I'm going to write my x plus 2 down twice. I'm going to come over to the side. And the only reason why I'm doing it on the side is because I know that some of you know shortcuts to get this part faster. Let's scoot it over a little bit. This means to take that x plus 2, write it down twice, and multiply it out. So I'm going to have x times x is going to give me x squared. Then x times a plus 2 will give me a plus 2x. Then I'm going to have plus 2 times x to get a plus 2x, and a plus 2 times a plus 2 to get a plus 4. So it'll look like this. X times x is x squared. X times 2 is 2x. 2 times x is 2x. 2 times 2 is 4. And now I'm going to combine my like terms. So I'm going to put the 2x with the other 2x to give me 4x. And so some of you know how to take that x plus 2 whole thing squared and quickly get that x squared plus 4x plus 4. So I'm okay with you doing that. Keep in mind, if you're not used to it, can I just not do this on the side and do it right here in the problem? Yes, you can. So I've taken care of that x plus 2 squared. That's that x squared plus 4x plus 4. Now I have to take care of that minus 10 times x plus 2. I've already said that that minus 10 is a negative 10. So I'm going to take the negative 10 and multiply by the parentheses x plus 2, which means I'm going to distribute. I'm going to get a negative 10x minus 20. Negative 10 times the plus 2 gives me a negative 20. And then I just get to copy down that negative 3. And now I have the fun of combining like terms. So I have a 4x and a minus 10x gives me a minus 6x. A 4 and a minus 20 is a negative 16. And then the negative 16 with the negative 3 is a negative 19. So I'm going to write minus 19. And that's my answer. Now let's cycle back over to number 2. For number 2, we have f of negative x. So this time when I write down the f function, wherever the x was, I'm going to put negative x. So I wrote it down with my parentheses, and I go back, and in the parentheses put a negative x. Well, a negative x squared is just a positive x squared, because a negative times a negative is a positive. And then that subtract 10 is a negative 10, so negative 10 times the negative x gives me a positive 10x. And then I just have that minus 3, and we're done. We'll have to evaluate f of negative x when we're trying to determine if functions are even or odd. When we're trying to determine if functions are even or odd, we're going to have to evaluate f of negative x. Let's look at number 4. On number 4, this time we're looking at f of x plus h. So in that f of x equation, wherever there was an x, I'm going to write my parentheses. And then inside the parentheses, I'm going to put the x plus h because that's what's inside the parentheses on an f of x notation. Now I'm going to work this similar to how we worked number 3. So I'm going to go ahead and go on the side. And take care of that x plus h, whole thing squared. I'll write it 2 times. I FOIL it out. So it's x squared plus xh, because x times x is x squared, x times h is xh, but we don't like to write it like that. We like to write the variable part up front. I'm going to write hx. Now I have to deal with that back half, the h times x, and the h times h. H times x is hx, and h times h is h squared. So now we obtain x squared plus 2hx's plus h squared. 1 apple plus 2 apples, 1 apple plus another apple gives me 2 apples. So let's go ahead and replace that with that x plus h in parentheses squared. Instead, I'm going to write x squared plus 2hx plus h squared. Again, this part I'm doing on the side, you can do it in the problem. Now I have to distribute that negative 10. So negative 10 times the x is negative 10x, and negative 10 times h is negative 10h, and I copy down that minus 3. From here, I'm going to combine like terms, and on this one, I don't have any terms to combine. I'm all done. We'll have to evaluate functions where we evaluate the f of x plus h when we're doing what's called the difference quotient. So we're doing that difference quotient, we're going to have to do this f of x plus h stuff. Now we can do the same kind of thing for numbers 5, 6, and 7 with the g of x notation. And we don't need to do 5 and 6 and then turn around and do 7. Actually, there was a reason why I had 5 and 6. So let's go ahead and do that. So on number 5, it was g of 2. And our g of x, this notation is what we want to use this time. So I find the one that says g, which is 4x cubed plus 1 all over x cubed. So wherever there was an x, I'll replace it with a 2. And we have this. So we're going to use our order of operations to clean this up. 2 cubed is what I have to calculate first. 2 cubed is 8. 8 times 4 is 32. 32 plus 1 is 33. And the denominator, we have 2 cubed. That's 8. So we have 33 over 8. It's an improper fraction, but it's okay because it's reduced. There's no factors that are common in both 33 and 8. that we can cancel out. So it's reduced to lowest terms. On number 6, instead, you see a g of -2. So it kind of looks like number 5, except, and in fact, let's do it this way. Let's take this. I'm cheating. I'm going to replace the 2 with a -2 in the parentheses. That's literally the difference. Where you had 2, you write a -2. So this time, when I take that -2 and cube it, I'm going to get a -8. -8 times 4 is a -32, and a -32 plus 1 is a -31. Then in my denominator, I have that -2 cubed, that's -8. Negative divided by a negative is a positive. So I have a positive 31 over 8. And that one too is reduced to lowest terms. So that one's finished. The reason for showing both the g of 2 and the g of -2 both side by side is so that you can see that even though the sign changed for the x, that doesn't automatically mean that your answer for y is just going to change by the sign. Okay? You have to go ahead and put it in. If it's an even on all of those exponents, yeah, you'll be okay, you'll get the same thing. If it's an odd on any of those exponents, odd exponent on any of those variables, you're not going to get the same thing. Odd exponent on any of the variables, you're not going to get the same thing. Even exponent on all of the variables, you'll get the same thing. And number 7 just had us playing around with that g of x notation just to get some practice on some crazy looking ones. Because we really don't like when stuff looks like fractions. Doesn't bother me, but for a lot of people it bothers them. So we need to see it so we can kind of get immune to it. And when I plug in that -x, it's going to look a lot like number 6, except it says -x instead of -2. So now I just have to consider my sign. A negative x cubed is going to give me a -x cubed. If it was a -x whole thing squared, like we had earlier, it became +x squared. But that's an odd on it. So when I have an odd on a negative, there's no type thing. And I have this odd exponent on this negative, I'm going to get a negative. So I'm going to have 4 times -x cubed to give me a -4x cubed plus my 1. And then the denominator I have a -x cubed. I'm okay with you all leaving the answer like this. But technically, we're not supposed to do that. We're not supposed to leave negatives in the denominator. I'm supposed to take this negative and bring it up here. So I'm going to take the negative and distribute it through the numerator. So that's going to change this from a -4x to +4x cubed, and the +1 to a -1. Again, we don't like negatives in the denominator. So either one of those will work because typically in these courses, we don't have tons of mathematicians and engineering majors taking it where I need to force them to move that negative from the denominator. And that is our function notation and evaluating functions.